Just to recap on what we have done, Newton's first law, just to make sure that everyone is in the right board, because there's no point going to problems if you don't know the basic ideas of the Newton's laws. The Newton's laws by themselves are very easy, straightforward, but how you apply depends on your understanding of these laws, proper understanding of the laws. It's easy to kind of quote these laws pretty easily, but when it comes to problem solving, you need to solve it by your thinking, by properly understanding what is being asked and how the laws are actually coming in. How do you tackle this problem and so on. So just don't memorize stuff. Physics is a subject that should never be memorized. It should be just understood and use your reasoning skills and logic skills to go through the answers. If you try to adopt a method of memorizing stuff, that won't get you anywhere. I've had many students in the past, like, not past, even now also. Like if a question is worded differently, and all that they're looking for is a formula. I need a formula to work on. Okay? And I need numbers. I need numbers and I need formula. Now all I have to do is either multiply or divide. That's kind of, I know students have, some of them are like that. For example, if I'm going to ask you, if a 25-year-old boy who weighs 600 newtons is sitting on a chair, what is his mass? What's his mass? A 25-year-old boy is sitting on a chair of whose weight is 600 newtons, sitting on a chair. What is his mass? Yeah.
600 divided by 9.
That's all you have to do. Now there are students who look at 25 and 600. What do we do with this? Multiply or divide? Just go ahead and multiply. Or just go ahead and divide. And then get an answer which is totally rubbish. Or another form of the same question. A 600 Newton person or athlete. A 600 Newton athlete is running at 2 meters per second. What is his mass? So again, 600 divided by 9.8. Why do you have to worry about whether he's running or at rest or dead or alive? You don't have to worry about any of these things. You just know, okay, 600 newtons of weight. That's his weight is equal to mg, and you have the answer right there. So you don't have to, basically what I'm trying to say is, you have to easily go ahead and find out what exactly is being asked and what concepts are being applied. Don't just look for equations. If you look for equations all the time and try to connect those numbers, what is the equation connecting weight and velocity? I don't know, and you kind of break your head, weight and velocity. I don't think I have come across, I don't know, maybe this, maybe that. And finally pull in some equation with velocity in it, plug in numbers, and get a wrong answer. So try to understand what is weight. Weight is a gravitational force. Just like F is equal to ma, it is weight is equal to mg. Right? So use your reasoning skills, use your concepts to answer the questions. If you are approaching physics in that manner, you'll find physics to be really enjoyable. But if you try to tackle physics by memorization or previous experience of solving similar problems, that won't get you anywhere. Okay? Try to adopt the method of not memorizing it. So that's why physics, to study physics for exams and all that, requires the least effort at home. Most of it is understood here in class. 99.9% of the understanding of physics is right here. What are you going to spend at home for? What are you going to do? Are you going to memorize the equation? No, actually none of those equations need to be memorized. So it's not the equations that are supposed to be bothering you. It is the understanding. And your understanding should be right here. So again, Newton's first law. What does it say? Net force equal to 0 means the object is in equilibrium. Another word for net force equal to 0 is equilibrium. And when an object is in equilibrium or when the net force is 0, two things can happen. Velocity can be either 0 or velocity can be a constant. Now some of you have just not taken proper notes. I can see the differences between your notes. The notes, some of you taking it very, very clearly and almost better than what I'm doing here. And some of you have very little written in your books. How is that going to help you review the material yourself? So make sure you take down notes properly. Because, when I'm actually showing you one problem, and then I change that problem to a different problem, you are changing it on your paper as well, which is not right. You have to take it as a different problem. You don't like make changes to your existing diagram and then finally. So you will find is just one problem, which is like jumbled up with many things being asked. So try to write notes as best as you can. Okay. Newton's third law says action and reaction pairs. Forces come in pairs. No force comes into existence alone. They are always coming in pairs. That is what Newton's third law is stressing. And those pairs have to be equal in magnitude, opposite in direction, must be of the same kind. And then act at the same time, act in the same line of action. And the last one is act on different bodies. If all the first five are right, but it is acting on the same body, then it is not pairs. Like for example, Michael is here. I am pushing Michael with 100 newtons that way, and he's pushing Michael with 100 newtons this way. Are they equal in magnitude? Opposite in direction? Same kind of force? Acting at the same time possibly? Acting in the same line of action? Acting on different objects? No. The last thing kills it. So those two are not pairs because they're acting on the same object. So unless all those 6 points are really satisfied, only then you can conclude they are Newton's third law pairs. Clear? And then the second law. The second law is just the opposite of the first law. First law says if the net force is zero, then what? And second law says if the net force is a finite quantity, positive or negative, doesn't matter. If it is a finite quantity, then what will happen to the object? The object is going to accelerate. Now if the net force is going to be in that direction, then it's going to accelerate in that direction. If the net force is going to be in this direction, then it's going to accelerate in this direction. That being said, suppose a car is moving in this direction. A car is moving in the positive direction, and it experiences a net force in that direction. What will happen to the car? It will decelerate, which means basically it's accelerating in the negative direction. Make sense? So try to understand it in the real concept, in terms of concepts. Okay, try to understand it that way. Again, when the net force is not zero, the object is going to accelerate, and that acceleration is directly proportional to the net force applied, and it is supposed to be acting in the same direction as the net force. The acceleration is supposed to be in the same direction as the net force, and it also depends on inertia. And so inertia, which is mass and acceleration are inversely proportional by themselves. The final equation that we ended up getting is F is equal to ma, where F is measured in newtons. That's why we don't use the K anymore. Okay, so those are the laws of Newton, and how we apply these laws into problem solving is what is to be seen now. Yeah.
When will the test over this be?
Next week. I think it should be already on. It should be next week, pretty soon. If it is not on mastering, you should be able to see it. Okay, let's see. I will check it on. You may have two parts, one in mastering and one here, so you may have parts of it. Okay, I'll let you know. Let's finish this topic first. Now, what are the different kinds of forces that I went through? You actually went through all this very well. Kinds of forces. There are field forces, there are contact forces, and then there are forces such as tension, right? Tensional force is a force that is set up in an object. So if I pull this meter stick like that, there's a tension building up in the meter stick because I'm trying to stretch it. So there is a force that is building up in the meter stick. So it doesn't matter whether this object is solid or a cable or a rope. Tension can be set up anywhere. Okay, so there's a tension built up right there. You don't see the stretching effect because this is a solid. So it is stretching, but it's not visible because the four atoms are pretty close together, so a little bit of stretching is not visible to you. Unlike a rubber band, where a rubber band actually is made up of atoms or molecules that are coiled. They're coiled molecules. The atoms are like this, like a spring. So when you pull, they are basically uncoiling. That's why you see the stretching effect more than a solid. Yeah.
So when you have like a rubber band and it like breaks, is it because it's weaker in that area, not because tension is greater?
No, it's just because it became weaker in that particular spot. And it is not necessarily the middle. It can be anywhere. Wherever it's weak, that's a place where it will break. So you can apply a certain tension or a force somewhere, but where is it going to snap is purely something that you cannot detect. Like if I'm going to connect this to somewhere and connect this to somewhere and just start pulling it and pulling it and pulling it, where is it going to rip? We can't tell. Because this looks even to us, but there must be some kind of a pocket somewhere internally, which is the weak point, right? And that will be the place where it will break. So the breaking is because it is not able to withstand that force. So what is tension? Tension is a force that is set up in, and I think I already touched on that when I gave you this example, right? The downward force is 49 newtons, and the upward force is tension. And what is this tension doing to this block? It is pulling the block upward. What is the same tension doing to the ceiling? Downward. So the direction of the tension depends on what object you are referring to. So the tension over here, somebody was asking, what is the tension at that point? Which way it is? Now, which way it is depends on what object are you focused on. So when you are applying Newton's second law, you are going to be talking about one object, not so many objects at the same time. When you're applying Newton's laws, you apply those Newton's laws to one object at a time only, not to a collection of objects. So apply the laws only to one object. So if your focus is on this object, then the tension here is upward. If your focus is on this object, which is above it, it's going to be downward. So you did have some mastering questions where they were asking about directions and stuff like that. So that's basically trying to test you on this. So tension is a force that is built in a material. Let me ask you a question right now. Suppose I give you a rope. Okay? If I give you one end of the rope, if I'm pulling this rope with 1,000 newtons, and you are pulling the same rope with 1,000 newtons that way, what is the tension in the middle of the rope? 1,000. I'm applying 1,000 from here. I'm pulling with 1,000. Somebody else is pulling with 1,000 from that direction. What is the tension in the middle? Can it be zero? Not tensed at all?
No.
That's impossible. Imagine you're standing like this, and somebody's pulling your right hand that way with 1,000. Somebody's pulling your left hand with 1,000, and there's no tension in you. Absolutely calm. No, that's impossible. Zero is impossible. Now, tell me about what could be the tension. Is it 1,000 or 2,000?
Everywhere on the rope, your tension is the same.
Everywhere in the rope, the tension is the same. That tells you it is actually 1,000. That is 1,000, because when I'm holding the rope like this, somebody's pulling with 1,000 and I'm pulling with 1,000. The tension here is going to be 1,000. And you can understand it better now if I tell you something like this. Look, that person is pulling from there and I'm also pulling from there with 1,000. Slowly, I'll take this end of the rope onto a nail or something and tie it up. I'll just tie it up. So instead of me pulling, now it's a nail pulling. Now I'm not doing anything, but you are pulling on a rope which is connected to a nail. Right? So you are pulling with 1,000. The nail is pulling you this way with 1,000. The tension is 1,000. Make sense? Just like the ceiling. The ceiling was pulling with 1,000. This ceiling was pulling it with 49. Right? Ceiling was pulling the rope with 49 upward. Or the rope was pulling the ceiling down with 49. And so the object was also pulling on the rope with 49. So it is always 49. So tension in one rope is always going to be the same. If you have a single rope. Now sometimes the rope can have a mass. That may make things different, but most of the time you'll be told it's a light string, a massless rope, and so on. Yeah.
So what if one person's pulling I think we talked about this, but what if one person's pulling at like 100 and the other person's pulling at 200? What would be the tension?
So if I'm pulling with 100 and you're pulling with 200, now the net force is not going to be 0, so I'm not going to be at rest. According to second law, the net force is ma, right? The net force is going to be ma. So it's going to accelerate. Everything's going to move now. But on the move, the tension here is not 100, it's not 200. It's something different. And we need to find it out, and we will do it today. Okay? We will do it today. On the move, what is possibly the tension? Okay? I think we did it already.
Yeah, I feel like
The elevator? What was the tension when the elevator was accelerating downward?
Yeah, we did that.
And when the elevator was accelerating upwards? Didn't we do it? Was the tension different? Yeah. The tension was different in both cases. When it was accelerating upward and downward, that's totally different. So, the weight is 49 newtons, the tension is T, and what if it was accelerating downward at an acceleration of 2 meters per second square? What is going to be the tension? So, if you know that it is accelerating downward, then this force 49 must be bigger than this force tension. Therefore, you set up the equation net force is equal to ma on this object of 5 kilograms. What is the net force? I told you, you don't look at this one as minus because it's downward, and don't look at this as plus because it's upward. You can use that, but it will confuse you more as you go on. Okay? So sometimes you can have these forces at different angles, and then you will be confused, should I take it as positive, should I take it as negative, and all those things. So best thing to do is the greater minus the smaller is equal to the net force. So you know it's going to be moving downward, so this is bigger. So 49 minus T is equal to M. M is 5 kilograms times A is 2. And so tension is equal to 39 newtons. Tension is 39 newtons. Yeah.
So why is it 49 minus T?
49 minus T because this is bigger and that is smaller. And that means the bigger minus the smaller is causing the net force of ma. The net force is ma. This is our Newton's second law. The only equation you're going to use in this whole place, whole chapter, is this. But then how you reach there, that's more important. How you actually use it is more important. Yeah, the equation is simple. F is equal to ma. Anybody can say it. But how do you actually kind of use that equation appropriately? That's matter. Yes?
Could you do with the elevator accelerating 2 meters per second squared in the upward direction?
You can. So if it's going to accelerate upward, if it is going to accelerate upward at 2 meters per second squared, we know that there are two forces only acting on the block. Out of these two forces, looking at which way it is accelerating, can you judge which is bigger? That's bigger. So therefore, you say T minus 49 is equal to ma, which is 5a, 5 times 2. And then your tension is going to be 59 newtons. So as you're pulled up, it's going to be 59 newtons. What if it is accelerating downward at 9.8 newtons or meters per second squared? If it is accelerating downward at 9.8 meters per second squared, so which is greater, this or this? 49 should be greater. So 49 minus T is equal to ma. Net force is equal to ma. So 5 times 9.8. So you have 49 minus T is equal to 49. What is T? Tension is 0. That means what? This rope is actually going to be slack. The rope is basically not holding this at all. The block is floating. You understand? The block is experiencing weightlessness. So when something is going down, why is it going down at 9.8 meters per second squared? Because this cable broke. That's why it's falling at 9.8 meters per second squared. It is falling now. It's not a controlled movement downward. It is falling at 9.8. That is why when it is falling, everything inside is falling. And so this elevator is falling at 9.8. This 5 kilograms is also falling at 9.8. So there's no need for the tension to act. Tension is 0. Yeah.
What would happen if your tension's negative?
Tension can never be negative. In other words, what he's trying to say is if someone is pulling this elevator from the bottom after it snaps, then acceleration is going to be bigger than 9.8. If it's going to be bigger than 9.8, tension tends to be negative, but tension can never be negative. How can you create a negative tension in a rope? The rope is going to just, like, how can you squish the rope? Okay? So the rope is going to be more slack. In other words, this object is not going to be in that location, it's going to rise up. When the net force is negative, yeah, it's not going to be in this direction anymore. Yes.
What about if it was not a rope but a pole?
A
Would it
pole,
be
yeah, then
pressure?
it's going to cause a compression. It's going to cause a compression in the pole. Good question. Because this 5 kilogram object is trying to move upward now. It's trying to stay, Newton's first law, it wants to stay where it was. So, see for example, look at this marker. See, everything is with the marker. I teach nuclear physics with this marker. I teach kinematics with this marker. I teach heat with this marker. Projectiles, everything is with the marker. This will be a bullet and a gun at times. This can be a truck. I just noticed it recently that I was looking at some of those videos and I said, every time I'm pointing this marker, that's interesting. All right. Anyway, that's the easiest thing to point quickly. So that is, what is this? What did you say this was? No.
An elevator.
No, I was trying to get to something.
An elevator.
Oh no, this is my hands, of course. My hand and the marker is sitting on my hands. So what are the forces acting on the marker right now?
The contact force.
The contact force from my hands on the marker upward, and the other one is
Gravity.
the gravitational force, which is called the weight of the marker, is acting downward. So those are the two forces acting on it. And if the weight of this marker is, if the weight of the marker is 1 Newton, if the weight of the marker is 1 Newton, what is the normal reaction? 1 Newton. Okay, keep watching there then. Now, as I move my hand at a constant velocity, what do you know about those normal reaction? I'm moving at a constant velocity. Newton's. It's 1 Newton weight. Weight is not going to change. Weight is the same thing, 1 Newton. But what's the normal reaction when I'm moving at a constant velocity? It's 1 Newton. What about going down with a constant velocity? It's 1 Newton. What about if I accelerate upward with something? Then what would be the normal reaction? Greater than 1 Newton. Get it? What if I accelerated downward? It will be less than 1 Newton. What if I accelerate with 9.8?
Zero.
Like that. See? Did you see the marker almost floating? The marker was almost floating. That is, if I move my hands at 9.8. So can you move your hands at 9.8? Yeah, easy. It's like hand is falling. Your hand is just falling. Can you move your hand with an acceleration of double the acceleration of gravity? Yeah, look at that. I just moved my hand down so quickly that the marker is left alone. Marker is not left alone, marker is falling. But my hand fell faster. You get it? So I'm moving my hands at probably 20 meters per second square. And you can see my hand went so fast, it's not falling. It went so fast, but the marker is just falling with its own weight, with acceleration of 9.8. Do you get it? See how much the marker can teach you. A lot of things. Just a little example. All right, so what's happening is the marker is now relative to my hand is actually going upward. Relative to my hand is going upward. That's exactly what happens to this. If the elevator is going to fall with an acceleration more than 9.8 by some method, then this is going to fall with 9.8, but relative to the elevator, it will be seen to rise. Right? Okay. So yeah, thinking is important. That's what I'm stressing. It is the same F is equal to ma that we're going to use everywhere. But what is happening in different scenarios, in different situations, that is. So you understand tension pretty well. Now let's move into another force, such as friction. Because friction is something that's going to be there in most cases, right? So what is friction? Friction is a force that opposes motion. Friction is a force that opposes the motion. Well, friction is something that's very useful too. I told you about it, right? Friction is something that helps you walk. Friction is something that drives your car. So friction is something that drives the trains. If there's no traction between the wheels and the track, the train wheel will just keep spinning in its own place. It just keeps spinning. Some of the naughty experiments that we have done when I was like small. Because I had to cross a lot of railway lines to go to my school. So, that's not legal though, but, we had to really take the stairs, and it was a big bridge that takes me down there. But climbing on this bridge and then going all the way there and then getting down from the other side, there were at least 10 tracks which need to be crossed. That's a junction, so there are a lot of trains coming in. And in my time, when I was young, most of them were like steam engines, steam types. Diesel came later. Electric came much later. So India has a lot of biggest network of railways, basically. The longest railways and so on. Anyway, so when I crossed, I was small. It's a kind of challenge also when I cross, because we need to know where the trains are coming from. Where are they? Which track on, there are trains coming, and so we need to kind of keep watching as we cross the railway tracks and keep going. There are just parallel railway tracks. And you can see the tracks kind of branch here and there. So even if you see a train coming from somewhere, we don't know exactly whether it's going to go on that side or this side. We don't know. So it's kind of risky. I don't know how we all survived. Yeah, it is really, I'm thinking about it now. Will I let my own children do it? No way. No way. But those are times when we had to do it. I had to basically get up from my home. We had to walk a lot of distance, get to the station, take the train, get down, and then after we get down, we just jump, go off the platform, and then we start crossing the railway tracks now. Those are just railway tracks. There was no electricity at that time, so no problems. So it's just railway tracks. The only thing we have to take care is, are the trains coming? Are the trains coming? And sometimes we see some trains coming, so we stand in the middle of not the middle of two tracks, between two lines. You know what I'm saying? So this is a railway track. This is another railway track. The gap is not too much, but yeah, we'll stand there and hoping to, trying to find out where it is going. So when you know that it is going behind us, then we start moving forward. Okay, so it's a kind of risky thing. So we stand here and wait for that train because there are a lot of ways that train can actually move. So we want to see which one it is taking. Anyway, those are my experiences. So as we cross these railway tracks, we see these steam engines and we see the driver of the steam engine sitting there. And we will just ask, I don't know why, but this is what we normally used to do. Ask him for, can you give us some grease? Because he has a big tin of grease. Grease. Right? So he has a big tin of them because he needs it for his thing to work properly. So as soon as we ask him, we are little kids, so he just takes a paper and just takes a little bit of grease and gives it to us. And we take it. Sometimes we take it home and it's useful because we can put it on hinges and stuff like that, and then, like the noise kind of goes off. So we just asked him for some grease and he gives us the grease. But there were some naughty boys, I didn't do it, but there were some naughty ones in my group. As we were crossing, they'll get the grease and guess what they'll do? They'll put it under the wheels. They'll just go down under the wheels. The wheels are like the main wheels of the steam engine, the big ones, the driving ones. They just put the grease, stuff the grease on the gap and on both sides. And then we will just wait there to see what is going to happen next. And this guy is ready to go, and then he wants to accelerate. But what happens is the wheel is not going to get the traction from the lines, and so just wheel will spin like crazy because it's not able to establish the friction. You understand what I'm saying? It just spins, and finally it managed to get a little grip because the grease is gone by then. And then so my experiences, wild ones. Anyway, got it. So what is the force that drives a train? Friction. What is that which drives a car? Friction. Everything is friction based here now. You're running based on friction. If a football player has to run really well, he needs a good grip on the ground. So he needs proper shoes which has spikes, right? You can't just use a canvas shoes and run because it will be very slippery. So you need proper shoes to have a good traction. You need to grip and pull. So friction is something that is very, very essential. So as I said, when you walk, what is causing you to walk is friction. So what is walking? Friction. Yeah, what is exactly walking? You are trying to drag the ground backward by gripping the ground. You want to try and move the ground backward. That is your attempt. It's like a treadmill. You know the manual treadmill? You're trying to do what? Move the belt backwards. Are you successful? Yes. And so what will happen? What is the consequence? The belt keeps moving backward and you stay in the same spot. Relative to the belt, you're moving. Relative to the ground, you're not moving. Right? 1 second. Okay, he has done. He has done already. He's already done. He is done also. All right. Yeah, come back. What do you say? All right, so I was talking about walking. So when you're walking, you are trying to move the ground backward. That is basically what you're trying to do. And when you get the grip, either you move the ground backward just like a treadmill, or you move forward because that refuses to move backward. So when you're trying to drag the ground backward, you are pushing or you are trying to pull the ground backward. What's the third law of air? What is the ground doing to you? Pulling you forward. So you go forward. Now if you're successful in pulling the ground backward, then you stay in the same spot and the ground moves. But if you are actually like not successful in pulling the ground backward, then the force of reaction from the floor on your feet is what takes you forward. Get it? And in order to do that, you need to kind of lean forward as well. We'll see that later as to why. Because you can't just pull the feet like that and then you'll fall backward. Inertia once again. Right? Imagine you're standing on a rug and somebody pulls you forward. You're going to fall backward. But then if you know that he's going to pull and you kind of lean forward to compensate, you're fine. And that's pretty much what we do when you're running, when you're actually like walking. You kind of lean forward too at the same time. You can't just be straight like that and walk. It's impossible. You need to balance it up. All right. So walking. So have you seen the circus globes? Have you seen circus at all? No? Have you seen it in movies and all things like that? It's a globe. It's the earth. It's connected like that, and you'll see a tiger standing on top. A tiger is perched on top of this big ball, which is the earth. And then the tiger is walking on the earth. So basically what the tiger is doing is like grabbing the ground and pulling it backward. So the globe moves backward, and the tiger is always there on top, right? Haven't you seen those pets? Hamsters?
Yeah.
Hamsters doing the same thing but in a different way. It's the same thing. What is a hamster trying to do? Push the ground backward.
Yeah.
And it is successful because that thing is light. And so it stays in the same spot. But imagine you just suddenly stop that wheel. If you suddenly stop the wheel, what will happen to the hamster? It will climb. It will climb. Because the force is always there. Right. So what is the tiger trying to do? The tiger is trying to roll this globe backwards, and the tiger is successful in doing so, and it stays in the same spot. We are also like little tigers on this massive earth. Now what are we trying to do to reach this spot? To reach this spot, what we're trying to do is we're trying to move the earth backward so that we can get to that spot. So my definition of walking is this: man, in an attempt to move the earth backward, fails miserably, and as a consequence, moves forward. That is walking.
Yeah. Well done.
Okay? So that is our walking. Why we end up going forward is this. We're trying to roll the earth backward so that we can reach that spot, but instead of the earth rolling backwards, we just end up moving forward because we fail in doing that. All right, so friction is a very, very important aspect. It is needed for things, and it is at the same time very bad. It's also very bad because it actually is opposing the motion. So when you think of a car moving on a road, most of the gas that is spent is to fight air resistance. Most of the gas that you're spending in driving the car is actually air resistance. So if the air resistance is lesser and lesser, you have better mileage. You have better mileage. Yes, I think I talked about it. Now friction, let's go into friction and find out what exactly is happening in friction. Friction, there's two kinds. Solid friction and fluid friction. Solid friction and fluid friction, these are the two kinds of frictions. And what is a solid friction? It is when one solid moves against the other solid. A solid moving over another solid. As two solid surfaces rubbing against each other, that is a solid friction. Two solid surfaces rubbing against each other, that is called solid friction. Two solid surfaces moving against each other. That is called solid friction. And then we have a fluid friction where you have a fluid in which another. So basically, it's a friction offered by one layer of fluid on another layer of fluid. It's a layer by layer concept here. There are two layers of fluid. What's a fluid? Anything that can flow, which is like air, is a fluid. All gases are fluids. All liquids are fluids. Okay? So fluid is either a liquid or air. So what's happening? Look at this marker again. What is around this marker is air, correct? When I move this marker, there is a layer of air stuck on the marker. It is bound to the marker. There is a layer of air stuck to the marker. And watch that layer with these layers here, which are stagnant. So when I move the marker, there's a layer on the marker which is rubbing against the other layer. See it? Hard to visualize, but that's what it is. So there's a layer of air on the marker which is rubbing against the other layer of air, and that causes friction. We call it drag forces. Drag. So when I try to move the marker is being opposed. By what? By that fluid friction. Do you get it? Whereas over here, it is between the two solid surfaces. So one solid surface move against another solid surface. So what is exactly happening over here is this surface has a lot of unevenness. And this surface also has unevenness. And the two uneven surfaces, when they're joined together, it causes the atoms to kind of cling on to each other like this, right? For us, it looks like something smooth, like this table appears to be smooth for our eyes, but if you zoom it in really, really well, you'll see all the strands of atoms like grass. This will look like a grass field. If you zoom it really well to atomic scales, you'll see that this thing is like a grass field, and another object, the book surface, is also like another grass field. Now the two fields are rubbing against each other. That's what it is. It's like two carpets placed like that, and then you try to move one. It's so tough. Why? Because when you put two carpets over each other like that, it creates a lock. And so when you're trying to drag the carpet, you're trying to kind of remove all the bonding, which is why it is pretty tough. Or if it is just a smooth object which is sitting on a carpet, it is pretty easy to move because that lock is not much. So the friction between two solid surfaces is because of this gap. Now, this solid friction comes in two forms. One is static friction, and the other is kinetic friction. Two kinds of friction, static friction and kinetic friction. In this, there is no difference. Fluid friction is just one kind. Static friction and kinetic friction. Now, what is the static friction and kinetic friction? Static friction is when the object is not moving, and kinetic friction is on the go. When the object is already moving, then that is called kinetic friction. When the object is not moving, then that is static friction. So let's look at it on an atomic scale. On an atomic scale, look at this. I'm looking at this solid surface. It's not moving. So when it's not moving, what's happening to those atoms? They are kind of clinging onto each other pretty well and locked up, right? So when I try to drag those two objects, what is happening is you're pulling the atoms and trying to stretch those strings or strands. You're trying to cause, so when I'm trying to pull this from here, this is trying to refuse, and that is a frictional force. So, but once you reach a certain point, it kind of breaks off, right? But once it's broken off, to re-establish the contact is tough. So once it starts moving, can the atoms hold as well as it used to? No, that is kinetic friction. So kinetic friction is never greater than this. This is the largest friction. Kinetic friction is always smaller. Why? Because on the go you cannot apply the same force that you could apply earlier. A simple example is a tug-of-war. Think of the tug-of-war. And suppose you're not moving. One team is not moving at all. Like they're firmly planted on the ground, and all of them are firmly planted, not moving. And can they apply a big force? Yes. But imagine the other team is a little stronger, and therefore what's happening is the rope is going. Because they are stronger, the rope is moving that way. And what you have to do, you can't just stay like that because you're leaning. What do you do to pull better? You have to readjust, right? You got to readjust because you got to move. You can't stay in the same place and do this. How can you apply a force on this? So you have to readjust so that you can lean again. But while you're readjusting, weak point. All of them are readjusting. Can they apply the same force as they used to apply when they were still? No. So the moment you actually try to readjust, it's already over. So did you understand this part? That static friction is larger than kinetic friction? Static friction, Fs. Kinetic friction, Fk. So static friction, Fs, is greater than kinetic friction. Right? And the reason is very clear. When it is at rest, it can offer the most opposition. But on the go, it can never apply the same. It can never apply the same. Well, think of this. Imagine there's a fence. All right, there's a fence, and you're standing close to the fence. You're standing close to the fence, and your friend is pulling you because he wants you to come somewhere else, and you don't want to go. You don't want to go. So as soon as your friend starts pulling, what do? You will hold on to one of those fence bars, and then there is a pull. You are actually able to apply a lot of force to oppose your friend because you're firmly holding on to one of those things, right? Now what will happen, eventually, some of the friend also comes on and starts pulling you. Now it is 2 versus 1. That's going to be tough. So you still apply a lot of opposition, but the moment you fail, you're holding like this. The moment you kind of start, doing that, that's almost over. It's over. By this time, it's over. Now, what's going to happen? Eventually, your hand is going to come off. Once your hand is coming off, you still can apply some opposition by kind of holding the next one and the next one and the next one. But how well can you grip the next ones? On the go. You can just touch them basically. So can you apply the same force that you're applying when you're still? No. That's why I said static friction is greater than kinetic friction. And you can see that very clearly also in many cases. Now suppose there's a desk that needs to be moved. Suppose there's a desk that needs to be moved and you're applying a force on the desk. You have experienced this. But now try to bring that experience into the fact. When you're trying to push the desk does not listen, does not go on. See, for example, this book. I'm pushing the book. See, I'm pushing with 1 Newton. Oh, let's say I'm not pushing at all. I'm not pushing the book at all. All right? Let me pull this down so it'll be better. There you go. I'm pushing on the book. Oh, I'm not pushing on the book at all. What is the frictional force? What's the frictional force now? Is there a frictional force? No. Frictional force is a force that opposes motion. Frictional force won't come in unless you try to move it. You understand? If there is an attempt to move something, then only friction comes in. Why should there be a friction? Why should there be a force when there's nothing trying to move it? It's like, you get into a boxing ring. You don't start boxing unless there's an opposition. You can stay still. You don't have to start fighting with the air. So you just simply stay there until action comes in. So here's the action. I apply a 1 Newton force on the book right now. So when I apply a 1 Newton force on the book doesn't move. Reason. Is there friction now?
Yes.
How much? How much is the friction right now? I pushed with 1 Newton and the book is not moving. Is it 1 greater than 1?
Less.
Think of your first law. Think of your first law. Just don't go by. Now, if you say that frictional force should be greater than 1 this way, then it should be moving this way. Right? You're pushing this way and the book starts moving this way. That's strange. So, come back again. I apply 1 Newton and the book is not moving at rest. What is the frictional force? 1 Newton. Now I push with 2 Newtons. Still it is not moving. What's the friction now? And I push with 5 Newtons. Not moving. The friction is a force that actually builds up just to oppose the cause. Right? If there's no cause at all, then why should the friction be existing? So friction is building up. Friction is building up. The opposition is building up. Now, eventually, maybe, but there is a friction. The grip on the fence has a limit, right? The same way friction has its own limit. There's a maximum limit. So, suppose the limit is 10 newtons. Suppose the limit is 10 newtons. The moment you apply 10 newtons or less than 10 newtons, suppose it's 9 newtons, it's going to be 9 newtons friction. The moment you apply 10 newtons, you have reached the maximum friction that this can hold, and that is the beginning of its failure. So as soon as you apply 10 newtons like this, it starts slipping. And once it starts slipping, it is very easy to keep it going. So this desk was so hard to move, but the moment it starts slipping, it's so easy to keep it going. Have you felt it? Have you seen this effect?
Yeah.
It's a very common effect. To move it initially from its point of contact is so hard, but the moment it actually starts moving, it is so easy to keep it going. To keep it going is so easy. That means what? On the go, the book is offering not 10, but less than 10. You get it? So kinetic friction is smaller. So if you try to plot this whole thing on a graph, if you plot the whole thing on a graph, this is the frictional force. And this is applied force. This is the frictional force, and that's the applied force. So when I applied nothing at all, there is no friction. When I applied 1 Newton, there is a 1 Newton friction. When I apply 2 Newtons, there's a 2 Newton friction. So you'll see a 45-degree line. You'll see a 45-degree line because this force and this force are equal to each other. You get it, Michael? These two forces are equal to each other. And so when it reaches a certain spot, which is like I applied 10 Newtons, how much is this force? That is 10 Newtons. And that is the maximum it can hold. What happens if I fractionally increase more than 10, like 10.00001? The moment I cross that 10, friction cannot stay 10 because the object is now moving. And on the go, it can probably apply 8 Newtons or 7 Newtons. So on the go, this friction will drop to something new. So this is the force, this is 10, and let's say that is 8. So static friction is 10, kinetic friction is 8. So this is the force on the go. Now when you can apply any amount of force, but the friction cannot change any further. Get it? So we have 2 kinds of friction, static and kinetic. Taking it? Have you drawn this? Now what factors does friction depend on? Friction depends on what factors? What factors? Like between the book and the table. What is the friction depends on what factors?
Mass.
It does not depend on the mass.
Surface area?
It does not depend on surface area.
Wait.
It does not depend on weight.
The force you're applying to it?
The-
Applied force?
Applied force? No, I'm talking about the force of friction. Like when I have a body, like when I have an object like this, I'm applying a force forward. This is applied force.
Acceleration.
But there is a friction that is coming here. I'm talking about only the friction. I'm not talking about my applied force.
Acceleration.
No, not acceleration. Friction depends on what? I told you it doesn't depend on surface area, which means what? Which means if I move the book like this, it's the same friction that I'm experiencing as this.
Inertia.
Inertia, no, that's mass. No. Friction depends on what? Of course, one factor is the nature of the surfaces. That's true. Friction depends on nature of surfaces. What kind of surfaces are we talking about? Is it rubber against glass, or glass against glass, or rubber against rubber? Yeah, the nature of surface is very important. Yeah. What is the other factor? There's only one more factor. Okay, watch this. Look at the book. I'm pushing the book, and see the friction force? Can you see the friction force that the book is offering on me? Now watch the same thing again. I'm pushing. It's applying so much frictional force now. So what factor was changed? Right there.
Direction of the net forces. Or force applied.
I didn't change the weight of the book.
Force applied. To
I didn't change the weight of the book. I didn't change the mass of the book. I didn't change anything that you're saying, the area, nothing. But friction is different now. Friction is different now. Okay, think of your hand. You keep your hand on a surface and slide it. See how much friction you're experiencing right now? Sliding it. Now, push it harder and slide it. It's so tough. Push it harder and slide it. It's so tough. What is the factor there?
Pressure.
Somebody tell me that answer, please.
Pressure.
Do you see the difference? The same hand. Very easy to move. Same hand. So tough to move it.
gravity.
What is changing between these two scenarios?
Force that is applied. Force applied.
Force, what applied?
That from the hand.
Downward force.
The force that one object
The force?
that one object
Which force? That's my question. It's a normal reaction. So friction depends on normal reaction. And nothing else. These are the only two factors for static friction.